So, question number 5. Right here, we are given a spring. Oh, all right. Okay. Question number 5. We're given a ball dangling on like a string, right? There's like a spring and like a ball dangling on it, and now the spring is being twirled around, and as you can see with a constant speed over here. Now, the distance from the spring is now 10.8. While before the spring was even moved, it was only 8.5 centimeters. The length. So the length when the sphere is moving is increasing. And the question 5a is asking about why the length of the spring extends. So the reason why it extends is because if we draw the forces that's happening between the spring and the ball, we'd have the tension of the spring, which is indicated by the red arrows. The net force or the net tension of the spring is going directly to the spring itself. The net force happens because there's the force happens on the y and the x axis. So yeah, and then after that there's the weight that goes down, marked by the green arrow, right there, marked by the green arrow. Now the reason why the spring is extended when you move it around is because the only force that are like the only force that's interacting with the weight is the vertical component of the tension, the vertical component of the tension from the spring. That's the only force that's interacting directly with the weight, with Fy, because the weight over here is only acting in Fy. It's not acting in Fx. It's not interacting with the net force. Is acting with the y-axis, or like the vertical component of the tension, and that tension, that the vertical tension, it's equals to the weight, because sigma Fy in here is basically 0, because it maintains the length. So sigma Fy is 0. Uh, 5b, the angle between the linear axis of the spring and the vertical is 27 degrees. Just 27 degrees, right? And then show that the radius of the circle is 4.9 centimeters. So how we can find the radius of the circle with just the angle? We can use the formula of if I'm not wrong, it's the theta is equals to no, sorry, it's the distance is equals to theta times r. So we can find the radius of the spring by r is equals to, wait, hang on. Oh wait, actually, never mind. We find this by the length of the spring is basically acting as the hypotenuse in here. You see this is making like some sort of triangle, you know, and then we have the radius over here. Hang on, let me annotate. So this is the spring, right? This is the spring length, and then this is the spring radius. And then like we have this over here. Now this is kind of shaping like a triangle shape. If it's shaping a triangle shape, then we can use the trigonometry sin cos tan, since the radius is the opposite from the angle. We use sine theta is equals to opposite over adjacent, so which is basically this. Sine 27 is equals to the radius over the hypotenuse, which is the length of the spring, and after calculation we get 4.9 centimeters, which is the radius. Show the tension in the spring, that the tension in the spring is 3.2. So we know the radius. We know the radius. Now we're finding the tension. So tension, like I said before. So tension. If we look at the forces over here, only tension that can interact with the weight is the y-axis tension. And as I said earlier, since the length is constant, that means it's not changing, not going up or down. That means sigma Fy is just 0. If sigma Fy is 0, that means the tension and the weight is the same. So with that being said, T cos 27 minus the weight, because this is 27 degrees. Hang on. This right here, 27 degrees. And we're trying to find this one, Ty. If this is 27 degrees, that means this is 27 degrees. And since Ty is adjacent with the angle, then we use the cos theta times cos theta times the tension, the original tension. And then we put that in, minus weight, T, that means T cos 27 would be equals to weight, and that means T is equals to weight over cos 27. The weight here we can find because I forgot to mention this. There is we are given the mass over here, 0.29 kilograms. That's the sphere. So 0.29 kilograms times 9.8 as given right here, and then after calculation, a bit of rounding, we get 3.2 newtons. That's the tension of the spring. Now, the spring here obeys Hooke's law. Calculate the spring constant in Newton per centimeters of the spring. So, Hooke's law, basically delta T is equals to the constant of the spring times the difference of the spring length. Basically, when the spring extends and or maybe let's say the delta x when the spring is normal and when the spring is extending, we just calculate the length differences of the spring, and then we calculate the force difference, or the EPE, let's say. So we got the tension and then we know the weight. We just do 3.189 minus 0.29 times 9.8. that is basically and then we get this 10.8 minus 8.5, which we get 2.3 times the constant is equals to 3.189 minus 0.29 times 9.8. And so constant is basically just 3.189 minus 0.29 times 9.8 divided by 22.3, which later you can get is 0.15. 5C. Use the information from B to determine the centripetal acceleration. Now, centripetal acceleration, the formula is v squared over r. So yeah, that's centripetal acceleration, and we use F is equals to ma, just that the acceleration is changed with centripetal acceleration, because the force here is the one that's keeping the ball in, like the tension goes, okay, wait, see the tension goes, hang on, so the tension goes this way, right? If we have sigma F is equals to m times AC, then that one goes the other way. This is the centripetal force that's keeping it intact as well, or like keeping the spring intact. Right. So with that being said, oops. So with that being said, sigma fx is equals to mac. Sigma fx, there's only one force that's acting on the x. That's acting on the x-axis, which is the tension. So t sine 27 is equals to 0.29 times acceleration. So 3.189 sine 27 is equals to 0.29, and then after that we can find AC, which is 4.99 or 5 meters per second square. And then finally 5C2, calculate the period of the motion. So the period of the motion we can find from the angular acceleration. Wait, yeah, the angular, wait, or like we can say like the W. The W is basically just 2 pi over the period. So that means we can find and we can also find the W from velocity, because velocity is W times the radius. So with that being said, AC is equal to v squared over r. V, the velocity, we can change to W times the radius. W times radius squared, meaning W squared r squared divided by r. So that means W squared times r, because one of the r cancels. So we we just substitute the one that we have, which is the centripetal acceleration and the radius. And after a bit of calculation, we got the W, or the angular the W. Now the W, as I said before, 2 pi over t. 2 pi over t is equals to 10.09, and t is basically just 2 pi over 10.09 over here. And that equates to 0.62 seconds. Right.
Oh wait, yes. I don't think we have enough time. So just one number.
Just one number.
Just one number.
Okay.
We'll go to the next.
All right.